Good morning. As you get into your reading and homework about the photoelectric effect and Einstein's very simple explanation for this phenomenon in the year 1905, it's helpful to have some background information about Planck's constant and where that number came from and what Planck did around the turn of the 19th, 20th centuries, somewhere around the year 1900. So I'll remind you of the definition of blackbody radiation. A blackbody radiator is an idealization. It's an object that absorbs 100% of the radiation incident upon it, and when brought to a very high temperature, does the opposite, emits radiation very efficiently across the entire electromagnetic spectrum. And the two most common or best examples of blackbody radiators that come to my mind would be the filament of a light bulb, because we're familiar with the light that it puts out, but also the surface of a star. So here's a little graphic showing you the profile of radiation emitted by the surface of stars at various temperatures. And there's a couple observations you can make here. The very hottest star here, 18,000 kelvins, that's quite a bit hotter than our star. It puts out more light at all wavelengths than the other two stars. So this is a graph of, they're calling it flux, but let's think of it as intensity, watts per square meter. It puts out the greatest intensity at something like 400 nanometers, but it puts out more intensity at all wavelengths than do the other stars. So that's the first observation. But the other observation, of course, is that the peak of the curve moves towards shorter wavelengths as you increase the temperature. So this red star here, which is only at 4,000 kelvins, that's cooler than our star. Our sun is around 6,000 kelvins. I think it's more like 5,800. Its peak is probably at the very edge of the visible spectrum, the reddest red that you can see. Any star cooler than that would have a peak somewhere in the infrared. In fact, not a star, but an object at, let's say, 1,000 kelvins or even 300 kelvins, which is about the temperature of your body, its peak would be way over here. So you are radiating. Your skin puts off electromagnetic radiation merely, by virtue of its temperature, but the peak of that radiation is far into the infrared, which is why we don't glow in the dark, at least not to ourselves, but perhaps another animal that could see in the infrared part of the spectrum would see us glowing in the dark. So Planck was very interested in the prediction of these curves. Nobody had successfully accounted for the shape of this curve theoretically during the 1800s, and this is something he took up in his career. And we've talked about this before, but one way of thinking about the ideal black body would be just a box with a hole in it. So a cavity that you bring to some temperature T. And it was known in the 1800s that matter has a charge within it, electric charge. It's a neutral matter as a combination of positive and negative electric charge. They didn't really know necessarily about atoms yet. That was what unfolded in the early 1900s. But they knew that matter consisted of charges, and according to Maxwell's electromagnetic theory, if you accelerate charges, you can expect them to emit electromagnetic waves. So if you've got electric charges within the walls of this box, and they're all jiggling back and forth due to their thermal agitation, then they should be emitting waves. And those waves would be bouncing around inside the box, absorbed and reflected in all different directions. And some of that electromagnetic energy is going to make its way out of the hole. And you would expect to see energy across the spectrum. But the profile of this curve is what was not explained sufficiently at that time. So in order to understand this, we'll think about it slightly differently than the way Planck thought about it. I don't know too much about the history, but I do recall reading that Planck made a different argument, a subtly different argument than the one that that's more accessible, the one that we'll talk about here. So you can imagine that there are standing electromagnetic waves within this cavity. And we studied standing waves early in the semester. Mostly, we talked about mechanical waves on a string, like the standing waves that exist on a guitar string. And we've got these various modes of oscillation. This is the so-called fundamental mode. It's got one antinode. This is the second harmonic, which has 2 antinodes. And as you move down here through this series of modes, you're talking about higher and higher frequencies of oscillation. So this is just a symbolic picture for an electromagnetic wave. You can't see an electromagnetic wave like this from the side, but the height of the curve here would represent the strength of the electric field. So if this was a standing E&M wave within a cavity, the node here indicates that the amplitude of the electric and magnetic fields, those oscillating fields, the amplitude there would be 0. You would expect to find no energy density there. Right here is where the amplitude is largest. So the electric field would be going up and down with the greatest amplitude. And standing waves are closely related to the notion of a simple harmonic oscillator, which is something you may not have talked about a lot in 3A, especially if you took it with me, because I always seem to run out of time before we get to that point in the semester. So let's go back to a little simulation here of a simple harmonic oscillator. The first one that you study in physics is the mass on a spring, the simple mass on a spring. So this is a Hooke's law spring with the stiffness K. And can I reset this here? Where's the reset button? I don't see the reset button. Okay, browser refresh works. I'm going to take a mass, plop it onto one of the springs. Well, that didn't work. How did I do this the first time? Come on, get on there. Not off to a great start here. Okay, there we go. Now, all I did was plop this mass onto the spring, and you can see the oscillations are already dying out. And that's because the simulation here includes friction. They've modeled the spring as including friction within the coil. So I can turn the friction off, grab this, I'm left clicking, pull it down. And so I've now put energy into this oscillator by stretching it. When I let go, it's going to bounce up and it'll bounce back down, but it will never bounce lower than the current position. That current position is what we call the amplitude. So there it goes. The total mechanical energy with which I endowed the spring, it consists of kinetic and potential. And energy is constantly being shuttled back and forth between those 2 types of energy. So when it's all the way down at the bottom for a moment, let me see if I can pause it at the bottom. Yeah, right here at the bottom, it's not moving for a moment because it has to turn around. So the energy is 100% potential. And then as it passes through equilibrium here, it's not stretched at all, so there's no potential energy. All the energy is kinetic. So it's constantly exchanging energy between those 2 types. And if I want to put more energy into the system, all I have to do is stretch it further. So the relevant point here in the simulation that I wanted to make would be, and let me restart this again, is that the possible energy possessed by one of these simple harmonic oscillators is a continuous variable. So presumably if you wanted to give this harmonic oscillator, I don't know, 2.000 joules, you could hang the mass on here. Stop. How do I grab that? And pull it to just the right amplitude so that its energy is 2.000, whatever you want it to be. Get rid of the friction. Now, supposing you wanted to give the oscillator 2.00001 joules of energy, all you would have to do is just pull it a little bit farther, whatever the appropriate amount is, according to the formula. So the thinking is that a simple harmonic oscillator can have any energy desired. The possible energies, it's a continuous spectrum. There's no limitations there on the possible energies. And you can also see that in the formula, which I'll show you in a moment. Here it is. M is the mass of whatever's hanging from the spring. Omega is the frequency of oscillation. It's how many radians per second you're cycling through. And A, of course, is the amplitude. Again, this is something you may not have learned in 3A. This is a graph of the spring potential energy versus displacement. So X equals 0 means the spring is neither stretched nor compressed, so no potential energy is stored. But as you move out to greater values of stretch, the potential energy rises quadratically with the displacement. That's true for a Hooke's law spring. Now, standing waves are really not simple harmonic oscillators, but they're very similar. In fact, for a wave on a string, every particle in the string is actually executing simple harmonic motion up and down. So while they may not be exactly the same, there's a close similarity there. So let's take a look at some video footage of actual standing waves on a string. Here's a guy in a physics lab classroom who has set up some standing waves with an oscillator and a piece of string. You can see we're in the second harmonic here. You can count 2 antinodes.
And we can see what happens if we keep going up in frequency. So this is still 22 hertz, and then we change to something like 25, 26 hertz, and we lose that resonance. Now let's go to 33 hertz, which will be the third mode of vibration. Here we are.
So there's a certain amount of energy stored in this mechanical standing wave. Now, you can imagine some of the energy is constantly being leached out of the system because, first of all, if you're near it and you can hear it, that means it's generating sound waves. Some of the mechanical energy is being lost to sound. Also, there would be some dissipation thermally. If you're stirring up the air, it should be getting a little bit warmer. There's got to be friction in the string itself and at the point of contact between the string and the support. So there's various ways in which the mechanical energy is being dissipated from the system. And yet the amplitude seems to be remaining constant. If I hit play here, you can see that. So how is the amplitude constant if energy is leaving? Well, that would have to be because the oscillator is continuing to replace that energy. It's doing work on the string as it jiggles it up and down. So the energy lost is equal to the energy replaced. It's kind of like when you ring a bell, you strike the bell, it's loud for a moment, and you can hear the volume decay because you're not replacing the energy that's leaving. Whereas like a violin, for instance, as you draw the bow across the string, if you just strike the string once with the bow, it might produce sound for a couple seconds, and then the sound decays away because the string stops vibrating as the energy is dissipated. But as you draw the bow across, you're continuing to put energy into the string and replace whatever's dissipated. And of course, the whole idea with the string is to dissipate that energy in sound waves. Okay, but I'm talking about the energy here because theoretically, in a classical world, you could put any amount of energy that you'd like into the standing wave. If you want to increase the amount of energy in the standing wave, you would just force the end here, the left end, to oscillate with a greater amplitude, because we know that the amplitude determines the energy stored. I think he's got one more mode here.
Again, I've stopped the video to do that.
There's the fourth harmonic. Okay, so let's look at a simulation once again. This website seems to be getting pretty popular, Desmos. There's a lot of great math tools on here. I haven't explored it much myself, but check it out. So here's a standing wave that they've actually produced mathematically by sending 2 traveling waves through each other, one to the right, one to the left. You can see all the mathematics here. This is something we looked at in depth early in the semester. They're using different notation than we use, but that's all they've done is produce 2 traveling waves passing through each other. We know that the result is a standing wave. Of course, that's only true if the amplitudes of the 2 waves are equal, which they are here. You can see amplitude 1 and amplitude 2. So if I want to increase the amount of energy stored in this standing wave, all I have to do is increase the amplitude. So I'm going to scoot these both one to the right. Now you can see the standing wave is oscillating with a greater amplitude. That would correspond to greater energy. Now here I was restricted to integer values, but hopefully you get the sense that you could increase the amplitude by any amount that you want, hence storing any desired energy. Classically, we think of the energy as a continuous variable. Now this is just a one-dimensional picture, but we're talking about standing electromagnetic waves in a cavity. And so this might be a more realistic representation. Here we've got a 3-dimensional object. And I think these are actually, this is the Falstad website, awesome website. You can see the little graphic down here. Is this Mr. Falstad? I've always wondered, is that actually him? Because it looks like he's got a mullet. This guy's I know he's definitely older than me, so maybe he was around at a time where that was socially acceptable. Mullets, the oldest haircut in history. Let's see here. Yeah, so I think this is actually representing an acoustic standing wave, like sound waves, but it works equally well for visualizing simple electromagnetic standing waves. And down here, you can choose the mode. In 3 dimensions, you kind of have to choose the wavelength along all 3 axes, so it's more complicated. But here's a different mode. But you can still see that there are nodes and antinodes. The colored regions, or the regions of dense color, correspond to antinodes, where you'd have a large amplitude oscillation and field energy, and the dark spots is where no energy. Those would be the nodes. So it's a 3-dimensional visualization of a standing wave. These are sort of the terms in which Planck was conceptualizing what was going on inside a black-body radiator. Now, again, he was actually more concerned with the oscillation of the charges in the particles of the box, not so much with the electromagnetic standing waves themselves. But I'm going to talk more about the electromagnetic standing waves. And so here is how scientists or physicists attempted to explain the profile of these curves, because that's what physics is about, right? Trying to come up with mathematical models that predict the reality of nature around you. And you begin by counting the number of possible modes within the box. So let me go back here. If electromagnetic waves can only be standing waves, like the ones you're looking at here, then you should be able to count them, because the condition is that, what is it? The length of the box, the width of the box has to be an integer number of half wavelengths. The condition's a little more complicated in 3 dimensions, but that's fine. So it's conceivable that you could count them. Now you end up having to use an integral to do that. You use something called the density of states, because of course, as these get shorter and shorter, I mean, how are you supposed to count all those? So you do it with an integral, but there is a way to do it, and I've seen it done. But hopefully this graphic gives you some sense that as you move to shorter and shorter wavelengths, the number of possible standing waves per unit wavelength gets greater. So it's like saying this, okay, how many standing waves are there that have a wavelength between 1 and 2 meters? How many possible standing waves are there in this box that have a wavelength between half a meter and 1 meter, or between 1/10 of a meter and 2/10? So as you get to shorter wavelengths, there are more possible standing waves that fit into the box per unit wavelength. Well, we know that short wavelength corresponds to high frequency. So right here, there's a little formula that's telling you the density of possible standing waves per unit frequency, and it's quadratic with the frequency. So that means as you move to higher and higher frequencies, in other words, shorter and shorter wavelengths, there are a greater number of standing waves per unit frequency that can exist in the box. That's how the density of states, so-called, depends on frequency. So that helps you count the number of states. And the idea is, and I'm sorry for switching back and forth here, the idea is if you can figure out the total energy in the box by counting the number of possible modes and the average energy in each mode, then you could relate that to the amount of energy streaming out of the whole. That's the whole idea. Figure out how much energy there is within the box per mode, per range of frequencies, and then that can allow you to calculate how much is streaming out of the hole. In other words, predict the profile of blackbody radiation. Okay, so the second part of that, first you have to count the number of states, then you have to figure out how much energy on average is in each state. Because if each of these states, modes, I'm using state and mode interchangeably, if each mode can have a range of energies, think back to the standing waves I just showed you, they can have a low amplitude oscillation or a high amplitude oscillation. If any possible amplitude is possible, and hence any possible energy is possible for each mode, you have to figure out what's the average energy in each mode. So in order to answer that question, some results were borrowed from classical statistical mechanics, which had already began to be developed in the 1800s. I forget when in the 1800s. But here's a result from classical statistical mechanics. It says that if you've got some system which is in thermal equilibrium with a larger system, like a much larger system. Remember the temperature reservoir? I've been talking about like a gas in a cylinder, and you put the cylinder in contact with a much larger thermal reservoir like the ocean, and that reservoir is at temperature T. When you go to measure the energy of that smaller system, there's a variety of energies in which you could find it. And I'm completely paraphrasing here, and this might not even be totally accurate because it's not something I've studied recently, but this is an almost ubiquitous formula in statistical mechanics. It says the probability of finding that smaller system to be at an energy E, the probability is proportional to this expression. This is an exponential function with the minus sign, so we know what that looks like, exponential drop off. And the greater the energy that you're talking about, the lower the probability. You see that? And the steepness with which this drops off depends on the temperature. And since T is in the denominator here, the greater the temperature, have I done this right? Let me think about this. Yes, I have. The greater the temperature, since it's in the denominator, the smaller the overall coefficient in front of E. And we know that if you have a small coefficient in front of your exponential variable, it will drop off less steeply. So I wish I had a graphic for you, but if capital T here, the absolute temperature, were higher, this would drop off more gradually, indicating that your probability of finding the system at the high energies goes up. And that makes sense. The hotter everything is, the more probability you should find, or the more likely it is that you should find the system at higher energies. Okay, so we don't need that for this class. I'm just giving this to you as background. This is one of the tools that was used to calculate the total energy bouncing around inside this black body. Count the number of modes, and then find the average energy in each mode using this tool, along with integral calculus. Okay, so that's what was done. I don't think Planck was the only person to have done it, but they kept hitting a wall. It was a dead end, because here is the actual curve, which describes the radiated intensity from a black body versus frequency. It's got a pronounced peak here, and then it drops down to 0 on both sides. But using the analysis that I just really paraphrased there, they found that at low frequencies, the curve should look like this. So if you count the number of modes and the energy per mode, you would find that the total energy radiated, per unit frequency should have this dependence, suggesting that it skyrockets. It shoots up to infinity as you approach higher frequencies. That doesn't make any sense, right? Like, according to this result, see how it's quadratic here? According to that result, the higher the frequency you're talking about, the more energy you should have coming out. And of course, that would mean quite a bit more violet light coming out of the hole than green light, even more ultraviolet light, and then X-rays. Well, I don't even know. Yeah, this is before they even had the term X-rays. But you get how ridiculous this is. That's not what actually happens. When you heat up a box to a particular temperature, an infinite amount of energy does not come out of the hole. And they were not able to reconcile their theoretical calculations with the actual curve. So this was really bothering Planck. This is what he was obsessed with at this point in his career. So he set out to see if he could explain this. So this graph, if you look carefully, this is intensity versus frequency. This is intensity versus wavelength. The shape of the curve is a little bit different, but no matter how you look at it, there's still a peak. Since we're now talking about wavelength, you can see that as you move to the left is when you get the so-called ultraviolet catastrophes. So the graph suggests that the theoretical calculations showed that the amount of energy emitted per unit wavelength shoots up to infinity as you go to shorter and shorter wavelengths. Remember, short wavelengths correspond to high frequency. Okay, here's Mr. Planck. Every picture you find of this guy, and everybody, it seems like at the time, they all look so serious and constipated, frankly. And I've read that it's because back then you had to sit for a while to take a photograph. I don't know if this is true. And who wants to hold a fake smile for like 2 minutes while they're taking the photograph? So nobody even tried. Okay, so I forget the quote exactly, but Max Planck said that his the solution that he arrived at, which really was the birth of quantum mechanics. Without this happy discovery, physics would have taken a little longer to get where it's at. That for him, it was just a desperate shot in the dark. He was just grabbing around, making guesses, really. He wasn't really necessarily guided by intuition. He was just trying to finagle the math to represent the experimental results accurately. Here's what he suggested. As you're looking at this, think back to those standing waves that I showed you, the string, the mechanical waves on the string, vibrating with a particular amplitude. He tried to amend the assumption that the standing wave could take on any possible energy. Rather than allow the energy of each mode, the possible energy of each mode, to be a continuous variable, he suggested, what if each standing wave mode can only take on a certain set of energies, like a ladder of energies. Like the standing wave can have this energy, or this energy, or this energy, but nothing in between, almost as if to suggest that only certain amplitudes are possible. So in other words, a discrete set of energies. And furthermore, the spacing of the energies depends on the frequency of the wave. So those the higher modes, like when I showed you the video of the mechanical waves on the string, the number 5 harmonic with the 5 antinodes, that string is vibrating at a higher frequency. So his guess was that maybe the spacing of the possible energies goes up as you move to standing waves with higher frequency. And again, not guided by intuition here. Who knows how many different things he tried before actually arriving at the fix to the math that led to an accurate representation of blackbody radiation. I don't know how he arrived at this, but it wasn't really from any theoretical consideration. It was just a guess, which is pretty awesome, right? And it encourages one in theoretical physics, I guess, to make similar desperate attempts. But how do we express that mathematically? Well, he suggested that the energy here can be some integer multiple of this fundamental unit. So the H here is really just a constant of proportionality. It describes the spacing of the energy levels. The fact that F is here, that's the frequency, tells us that the spacing is proportional to F. So at higher frequencies, the spacing goes up, but the exact spacing is going to depend on the value of this constant H. So just think of it this way. If plug in n equals 2, like if we're talking about the energy down here, this would be the second energy level. Plug in a 2, plug in a 3 to get this energy. Now what's the difference between those? 3 times HF minus 2 times HF. Well, that would just be 1 times HF. That's why the spacing here is HF. So the spacing goes up for higher values of F, but the actual value of the spacing is going to depend on this undetermined constant H. So all he had to do, it turns out, was to make that assumption and then go back to the business of counting the number of modes and calculating the average energy using the probability of each particular energy. But this time, the possible energies that went into the integral were discrete. It wasn't a continuous variable. So that changed the math a little bit. I've actually, once upon a time, I went through all the details of this calculation. It's really not too challenging. It's all applications of the calculus that you have already learned. There's some summations in there. So it's really cool to see the result. But when you do that integral, you leave the value of this constant of proportionality undetermined. H is undetermined. And what comes out can be matched with experiment. Remember the Stefan-Boltzmann law, the power radiated by an object is proportional to the 4th power of the temperature? That plays a role in fixing the value of H. So you just match the result of your integral calculation with experiment, and that would fix the value of H. And that's what Planck did. And you know what? I don't have it in the slides here, so I think I'll add that. There it is. This is called Planck's constant. We're going to see that Planck's constant allows us to calculate the energy of an individual packet of light energy, or a so-called quantum of light energy. Planck had no notion at the time of packets of light energy. In fact, from what I've read, he was really reluctant to accept that light came in little corpuscles of energy, which we now call photons. Einstein didn't call them photons at the time, but he didn't even like that explanation. And he's the one that discovered this darn number. That's really fascinating about science, is that an individual can spark a revolution. You know, it was their research that led to these new ways of thinking, and then they're reluctant to accept the consequences. I've encountered that theme a number of times in my limited reading about the history of science. So that's kind of encouraging, right? Because you bust your butt trying to learn this stuff, and then you find out that the person who developed it was being hard-nosed or stubborn about everything that came after. I don't know. Somehow that's encouraging to me. It's an extremely small number, is it not? So this number is fundamental in physics. There's the Planck length, the Planck unit of time. You need this number a lot to talk about physics at the scale of the atom, to talk about cosmology, the Big Bang. You're going to see this a lot, especially those of you who, let's say, study astrophysics or quantum mechanics in the future. And joule seconds, I believe, are the units of Planck's constant, and that's equivalent to angular momentum. Interesting. Why would this number have the units of angular momentum? Well, we're going to see that later in the chapter when we talk about the hydrogen atom, the Bohr model of the hydrogen atom. So this was a major moment in the history of physics, discovering that, and again, Planck's interpretation was a little different. He was talking about the oscillations of the atoms that made up the walls of the cavity. He was suggesting that those could only have, those harmonic oscillators could only have energies that took on a discrete set of values. Now it makes more sense to talk about the energy of the standing electromagnetic waves within the cavity. But it's really grainy. Here's the actual formula for the dependence of the intensity of light on wavelength. You don't need to know that, but now you've seen it. You know, it looks a little complicated, but it's not that bad. Lambda is for wavelength. There's his little constant there, h. Speed of light is c. Okay. And Boltzmann's constant k makes a little appearance. That's from statistical mechanics. And here we go. Here's the pre-Planck theoretical curve for how the intensity should depend on wavelength. Now this looks backwards. No, it doesn't. It doesn't. No, you can see how the ultraviolet catastrophe happens as you move to the left. That the intensity skyrockets at shorter wavelength. And the black curve, the one that peaks, would be the Planck, theoretical Planck curve. These white dots are experimental data points. So basically you would put a light-sensitive transducer, some kind of measuring device, right outside the hole of that black box. And all you would have to do is measure the intensity of light coming out at various wavelengths. That's something that was possible to do at that point in the history of physics. And then you would just compare those data points with the curve. So all Planck had to do is tweak the value of h until the theoretical curve matched the data. That's how we got that value.